So I'm just trying to create a more sophisticated example. So, question. Is there a pattern? Where is the pattern?
Being multiplied by -3.
Top is multiples of 3.
Well, -3, right? Or, well, either the top or
If you
bottom is
insist,
being
sometimes I can look
negative,
at it.
yeah.
Is there like a certain magical 3-step process to looking at a pattern, or it's
No,
just
I'm honest. There isn't one. And that's why I try to make more complex examples. Because sometimes it's just not that quick. Now, maybe upstairs is quick. I like what you guys said. That numerator neglecting sign changes seems to be increasing by a factor 3. Looks like it's growing geometrically. Or you might have said back at math D, it's growing exponentially. But what about the denominator?
2 times 4 is 8. 8 times
4 is 6, and 8.
Yeah, that's weird.
2, 6. 8 times 48. What's 8 times 48?
See, I think you guys are stalling. I think what you really should do is this. Can we skip the numerator? You seem to figure that out. Can we skip the sign change? You seem to figure that out. Let's concentrate on the denominator. When I glance at that, I don't see anything that quick. So can I show you what I do? I talk about one denominator time. Here's the first one. It's just a 2. Here's the second one, which is 2 times itself 3 times. Here's the third one, which is 48. But 48 is 2 times 24. 24 is 2 times 12. 12 is 2 times 6, but 6 is 2 times 3. Yeah, Deborah, I'm just panicking. I'm just writing prime factorizations. Is it what? Very nice. In fact, maybe there's a couple of them. When I look at the 84, that's 2 times 1, I don't know, 82? But 182 is 2 times. I think I misspoke, everybody.
192.
Is it 192? Thank you. I just caught it in my head. But, so 2 is, 384 is 2 times 192. But 192 is 2 times.
81.
Say
Or 91.
96.
96.
And 2 times 96 is 2 times.
48.
48 is 2 times.
24.
24 is 2 times.
12.
12 is 2 times.
6.
6 is 2 times.
3.
So let's try to find a pattern. See, 1 factor 2, 3, and then 4. It's not matching up, is it? 1 to 3 to 4. Then all the way to 1, 2, 3, 4, 5, 6, 7. That's not going to work. Kind of be nice if there's a nice clean progression of 2's living there. But I see maybe a sub-pattern there. I mean, look at 1 factor 2, then 2, then 3, and then 4 factors of 2. I mean, at least that's a sub-pattern, isn't it? And then what's left over is 2 or 2 times 3 or 2 times 3 times. And it's working. Because I think this 2 times 2 could be interpreted as this. Therefore, what you see inside this perfect circle is a 2, then 2 times 3, then 2 times 3 times 4, which kind of looks like a factorial. As a matter of fact, here's the 4th term. I see 4 factorial. Here I see 2 to the 4th. Here's the 3rd term. Downstairs I see a 3 factorial, 2 to the 3 power. Here's the 2nd term. I see a 2 factorial times 2 to the 2nd power. Here's the 1st term. I see a single power 2, but also times 1 factorial.
If you're doing a factorial, though, you can just use n as the first term, just times n.
You know, I can do that if I'm looking for a recursive formula. And maybe I did a poor job with this question. I just listed my sequence. What I really need to ask you is, can you give me an explicit formula for the other term?
I don't know if this is what you just said, but is there a pattern of 4, 6, and 8?
But where do you see the first 4?
The first 4 is 8 divided by 2.
And then
48 divided by 8 is 6. And
And
then that's 384 divided by 48 is 8. So maybe it's
I'll buy that, but the way you're saying it makes it difficult for me to identify what the nth term really is, because you're saying this divided by the predecessor or something. And when you say this divided by the predecessor, it just kind of reminds me that we're building some kind of recursive formula, or some kind of implicit description of the sequence, where I want something more explicit, saying, oh, jump here, plant your feet, the 12th term, can we determine what it exactly is without knowing what happened in the predecessor's case?
Can you derive one from the other, like the recursive from the
Ugh. That's a loaded question. The answer is yes. It's just that it becomes difficult without more background, and being able to do it with the sequences that maybe involve more than one predecessor with a recursive formula. And I'll discuss that rather heavily to give you really sophisticated long techniques in Math 15. If the college ever lets me teach you.
What if we start a petition?
Oh, absolutely.
All right.
So you guys, do you think this is good enough to write the pattern?
Yeah.
Maybe then the nth term of my sequence is described by, let's take care, can you take care of the negative sign first? Just get it out of the way. I'm serious, I always do this. I slap it down, see if it's right. With the very first term, when n is 1, is this going to be negative? It is. It is my first term negative.
No.
It's not, so how do you might change it?
Plus 1.
Plus 1 or minus 1 or plus 3 or minus 3, plus or minus any odd integer would work, right? And I think as far as the numerator is concerned, you guys already told me what's going on. This is 3 in the end. Yeah, I think I'm a little off. I think the first numerator has 2 factors of 3. The second term has 3 factors of 3. And then the third term 4 factors of 3. I think I need to increase my n by 1. But can you appreciate my thought process? As far as downstairs is concerned, well, let's just go by what we did in green. And green, I've got 2 to the... But what else I have in purple is...
N factorial.
I like it. Maybe you like to choose to combine those 2 bases in the numerator's position since they have the same exponents. I don't know. It's entirely up to you. I don't know which one looks better. But you guys see how lazy I was downstairs? I just factored and broke apart and see if I can find some subpactors in there. Make sense?
So in any of these, you basically just go back to the building blocks, kind of like if you're doing trig.
Unless you can see it right away, then go back to your basic building blocks, which is sort of what you did back in trig when you verified identities. You get stuck, got all the secants and tangents all over the place. Give up. Treat everything in terms of your basic building blocks and see what's going on. Same idea. What about my next example? Sorry, my next example has a question. What's the limit of a sub n as n increases up now? Okay, don't answer the question.
Yeah.
Just tell me how to.
Well, you can't. Yeah, you can't because there's a 0 in the denominator, so you need to resort to L'Hopital, right?
No, wait a minute. My question is, what's the limit of this beast?
Or not a
Does it
0.
increase that bound? And I think I'm...
Or it's undefined in the denominator, sorry, and the numerator, right?
And so I think everything's okay as n increase that bound.
Is it?
Because n increase that bound, this thing's going to 0. And so eventually I'm honing in on
Oh.
input for the tangent function of
I'm
0.
looking at it backwards.
But jeepers, that's going to give me a 0 over 0 situation. That screams out. That screams out.
L'Hopital.
L'Hopital's rule. And using L'Hopital's rule to take the limit, hold on. You guys, I'm losing it. Take the limit and increase that bound. I know it's my example, but I can't read that far. Tangent, like this, over this.
Yes.
And so using L'Hopital's rule, derivative tangent of anything is,
Well, can you
can I what?
n increases the bound? There's no n.
Oh, I'm so sorry. You're right, Deborah. There's no n. Time for me to fix things. I apologize. I didn't even see it. Now that I'm making sense, what do you think?
Okay. Well, wouldn't you have to replace it with
At
x
this
if you're
time I would,
doing
not
L'Hopital?
initially.
Yeah.
I think at this point I would have to think as the limit. As x increases the bound of the tangent of 1 over x to over 2 over... Why am I replacing n's with x's?
Because n is not continuous.
Well, I'm horribly discontinuous for a lot of endpoints.
Yeah.
You really mean because if I'm going to differentiate,
Yeah.
I need to have continuity, at least locally speaking. So, applying L'Hopital's rule, what do you think?
Negative 1 over x squared times secant squared of 1 over x.
All over.
All over negative 2 over x squared.
Tad bit of cancellation. And with a tad bit of cancellation, as x increases that bound, this input's going to 0. But as the input's going to 0, secant clearly goes to 1. And 1 divided by, oh, look at that, a constant. I think it's just going to give me 1 over that constant.
So if you have to state that x starts at 1.
To be honest with you, I don't know if I really care. Because what's happening is I'm eventually getting really, really big for x's. And that's where my concern is what's going on for large values of x. Do you think we could evaluate this limit without L'Hopital's rule?
I was confused about the converting the book. One of the examples, it leaves it in N.
Don't
and
tell me
uses-
that.
Uses L'Hopital's rule.
No.
They leave it in n throughout the
Show me,
entire
show me.
thing,
Don't
yeah.
say that.
538.
Oh, the 5 and the 3 cut up to the 8.
Yeah, I could show you the
Series.
answer book. They just leave it in n the entire time on all of them.
You're not going to do this in exam, are you?
No.
Because you don't want to do that. You would never differentiate something that's not a function on a continuous variable. You really would you?
Do they state that n is a continuous variable though? Because if they do that, it's legal, right?
Couldn't you just say if n is a continuous variable?
Yeah, just kind of do.
Or assuming n is a continuous
By Harry
variable?
Potter mathematics, n is a continuous variable, therefore math works.
You know, it's so frustrating. It's on, on the same page, if you go up to solution for example 1 part A, he does say f of n equals a n, and therefore f of x is all of a sudden x. And yet then he violates it in the very next example. I don't know why.
He might be drinking while he's writing that.
Yeah, drink while you're writing this.
Yeah.
I apologize, I really don't like that. It's really wrong. I hate to come to class saying don't do it that way. Ay, ay, ay. If you guys are okay with this, can I get rid of it? Give me another technique that works.
You just write out.
Yeah, but that means it seems to go to 0, but it's not a guarantee that it does. Yes, no? You don't like that.
What exactly would you do with that?
Oh, everything. Because now as n increase that bound, this input goes to
0?
0, but the denominator goes to 0. It's sort of like a sine of u over u as u goes to 0, but you guys already learned last semester, probably took a 25-minute argument geometrically, but the sine of u over u as u goes to 0 is going to be positive 1. And I think I'm just simply left with 1/2 times the limit of the first, which is 1. But as n increase that bound, this goes to 0, so the denominator goes to 1. So I think I can just get 1/2 for free. No, look, it's not. You guys have all seen this, right? The limit of the sine of z over z as z goes to 0 is equal to 1. You needed that to be able to prove that the derivative of the sine function is a cosine function. All right. So I'm assuming your Math 30 professor proved or derived it out of thin air. I know yours. So you guys, question. Here's a quick question. I don't want to write. I want you to give me the answer. What's the limit of a sub n as n goes to infinity?
What?
I agree. Why?
Because if you expand the top, then the coefficient of x squared
simply put, he's giving us a nice, clean Math 29, a pre-calculus answer. Looking upstairs and downstairs, those are two polynomials of the same degree. Can we imagine their x's for a minute? And so to graph y equals all this garbage and replace with an x, I think we've got a rational function that has a horizontal asymptote at the rate, y equals the ratio of leading coefficient upstairs, leading coefficient downstairs, which is clearly positive 1. Give me another thing.
What was the question?
What's the limit of case of n as n increases up bound?
Well, you would multiply everything by 1 over n squared, top and bottom.
Very nice. Span this garbage out. Multiply top and bottom by 1 over n to the power as high as you see downstairs, which is 2. Clean up and allow 1 over n as well as 1 over n squared to go to 0 as n increase that bound, and you're going to get the same answer. Give me a third technique.
Wait, isn't that the same as the first one?
It is the same as the first one.
I don't think so. I think a lot of you probably raised back in pre-calculus to say simply that if the degree upstairs is the same as downstairs through polynomial long division, not by multiplying 1 over n squared, through polynomial long division, you'll still get that the ratio of leading coefficients is the location of the horizontal asymptote. I don't have to use the 1 over n squared business to answer the question his way. Give me a third technique. L'Hopital's rule applied maybe a couple times. And you're going to end up eventually getting what? 2 over 2 in the end, which is still positive. Question. Is this sequence monotonic? If this is the term of the sequence, is the sequence monotonic? What does
Yes.
monotonic mean
No.
again?
Strictly goes up.
Strictly increasing or strictly
Decreasing.
decreasing. Is it monotonic? David, you're on the answer to the question. How do you know?
Well, because they're both n squared terms and they're both, I don't know, I'm just picturing two parabolas, and they're both increasing.
Well, if you think of these x's, I see a rational function with a couple vertical asymptotes. Oh, sorry, I misspoke. Potentially a couple vertical asymptotes. Not looking very carefully. In this example, it really does happen. And with vertical asymptotes, I do crazy stuff all over the place. Maybe not for values of n, 1 or bigger. But how do I determine if I'm monotonic?
Derivative.
Yeah, unless it's Bradley, unless it's like one of the homework questions you asked, where it's
Yeah.
pretty clear with exponential, or whatever, anything that's clear, fine. I think this example is unclear enough to where maybe I want to differentiate. And if I differentiate, I get this. Let's see, if y is equal to all that garbage but in terms of x, then I think y prime is what's downstairs. Times the derivative of what's upstairs. Minus what the heck I see upstairs. Times the derivative downstairs. All over what I see downstairs twice. Oh, that's upstairs, isn't it? I said downstairs twice. Next. Oh, you guys, you want me to put the 2 in first or multiply out?
Neither.
Neither. I'm tired. I'll use our math B skills instead. I feel so alone.
Maybe.
Yeah,
If you
just up
factor the
Factor the
leading term in the numerator, x squared plus
Yeah,
3x plus, yeah. Well,
and that tells me I have left over 2x squared plus 6x plus 4, and I don't know what else. Is that a minus 2x squared? Is that a plus 3x? Is that a positive 9? All over stuff. And if I combine like upstairs, like terms upstairs, look at that, the x squareds are gone. This isn't that bad. I got a little lucky. I do have 9 x's, and I don't know how many constants. Is that 13? It's 13. All over this. And if I were to build a sign graph of my first derivative function, see what I get. Here's my -2, here's my -1, here's my +3. Oh, I forgot something, my -13/9. So you guys, let's play. If I plug negative billion for x, let's see what the sign of the first derivative function is. Plugging a negative billion for x, this is clearly positive, this is positive, this is,
Negative.
I can't hear you,
Positive.
I can't hear you.
Nothing.
Remember, I cheated. I looked at a continuous function. I'm trying to figure out if my original sequence is monotonic. I only care about values of x, like the n's, that are at least as big as
Positive.
1. So, let's just check out what happens about x equals 3. I think to the right of that, don't do any work, clearly positive. To the left of it, choosing a number like 2.99999, when I plug it in here, I'm getting too much work. Look at how that's a 0 of a linear factor raised to an odd power. Clearly, that particular linear factor is going to act as a toggle switch. I know I'm going to get a sign change on either side of 3. Now, what does this really say to me? It says the original function changed from decreasing to increasing on either side of x equals 3, but that means the corresponding sequence defined for values of n1 on up changes from decreasing to increasing about n equals 3. Therefore, my particular sequence is not monotonic. I agree. I just thought my examples were too easy last time. I'm sorry. I had to go back. All right. If you're okay with that, then I think the one last thing I need to say about sequence, I really do need this, is the following. What if I have a sequence that's neither bounded above or bounded below? Do you think the limit of the nth term necessarily has to exist?
Yes.
So I think the answer should be no for this reason. Because I think if it's not bounded above or below, maybe a sub n increased that bound. As n increased that bound. Did you guys see my point? However, if the nth term of my sequence is bounded, would you guys agree that the sequence has to converge?
No.
Good. I'm glad you said no. I don't think it has to be true. Watch. Look at this particular sequence. I think it's bounded above and bounded below. But now if I steadily go back and forth about y equals whatever the L is, I think the limit does not exist. I don't think this particular sequence converges. Just because I'm bounded doesn't mean I converge. What if I'm monotonic? Here's the n-axis. And I'm strictly increasing. Do you think the limit of the nth term is going to be some fixed real number? Do you think the sequence has to converge?
No.
Yeah, I don't think so either. I still don't think I've got any guarantees here. One last attempt. N-axis. Suppose I'm bounded above by m, and I'm bounded below by, have a little m. And if I'm monotonic, strictly increasing or decreasing, do you think I must converge the sequence? I think I do. I think when I got a sequence that's both bounded and monotonic, I think that guarantees convergence. Let me say that officially. It's so important, I'll give it a name. Theorem. We'll make it official. If this particular sequence is both bounded and monotonic, then it converges. You guys, this isn't going to be some result you're going to be using every single day outside of class in the homework set. However, this is an extremely important theoretical result I need to be able to prove other things in class. Since it's that important, can I talk very briefly about why this is true? And as I'm getting ready, erasing my board, cleaning the mess up, you guys need to go back to my formal definition of convergence for a sequence. Say the limit a sub n goes to L as n increased that bound means this. No matter what epsilon is, I can find a big N so that if little n is at least bigger than big N, then this difference is less than epsilon. Now if I can establish that, I've got convergence for my sequence. So, proof. Without loss of generality, can I just pick one of these case scenarios with monotonicity? Let's suppose that this particular sequence is strictly increasing. It is bounded above. So, I think what that really means is that no matter what little n is, it's always strictly less than some limiting value, call it L. Let's suppose L is the least upper bound. For this particular sequence. Now that's kind of a stretch, you guys. When I say the least upper bound, it's just a quality that real numbers have. There's a name for that supposition. It's called a completeness axiom. Something we use to actually try to pin down what the real number system is. But if L is the smallest upper bound, then I think there exists some number, call it down, I got an idea, how big N? Going back to my definition. There exists a big N such that I think I can choose big N so that a sub big N is actually bigger than L minus epsilon. But my particular sequence is strictly increasing. So I think that necessarily means that a sub n, that's lowercase n, is at least as big as L minus epsilon for all values of little n that are at least as big as big N. Notice I'm tying into my definition. I set myself up. Now if I can conclude this is true for all little n being bigger than big N, then I think I've proven that the limit exists. And I think I've proven that I particularly converge in this case. So let's give it a shot. If I manipulate this inequality, if I bring the epsilon to the other side, does that suggest that L minus a sub n is less than epsilon? Oh shoot, that's backwards from what I have over here, isn't it? Actually, it is, because I think a sub n minus L is going to be positive. So, why don't we just force the issue? I think equivalently, a sub n minus L is strictly less than epsilon. Therefore, I do maintain that my particular sequence converges. And that is significant. By the way, I'm not really cheating, because technically speaking, since the sequence is increasing, this really is a positive number. So I really do think this is a strictly positive value. I really do have the right to rewrite that in terms of inequality. So you guys, this is significant. So significant, let me talk about sequences. Sorry, I just said sequences. I meant to say, let me talk about something different. Series.
Are we gonna have to learn this proof?
What's the word after proof?
Yeah.
Wow. Without lack of generality.
Yeah, WLOG. I didn't make that up. We use that abbreviation all the time. It just means without loss of generality. Do you see why I'm saying that, Linda? Because watch, when you look at my proof, I was supposing that my sequence is increasing. I think my proof's going to be very similar if my sequence is strictly decreasing. I'm just going to reverse some of the inequalities. And that's why we use the phrase without loss of generality. The other portion of the proof should be.
And then it says AN is less than L, and then what is that abbreviation between the two capital L's?
Suppose ST.
That's pretty.
Come on, you guys attack me. Did I talk too much? Did I talk too fast at me? Because you can nail me on this. I did. I feel bad, Deborah, because it really is so fundamentally important in terms of our test for convergence I'm going to be discussing. It's really a big deal. Maybe not a big deal for you to put in your back pocket as a tool, but a big deal theoretically.
So is this something we're gonna have to learn for a test, or?
What do you mean, is this something?
Well, are we gonna have to learn this proof?
Are you gonna ask us to recite it?
I think that's horribly unfair for me to do for this reason. That is well beyond the scope of this course. I really did hand waving. How the heck are we guaranteed that there is a least upper bound for this particular set of things called the ace of L's? I am guaranteed it, but it's certainly beyond the course, beyond the scope of this course to say or proclaim that that's going to be true. So no, I would not for that reason. Yes, Tyler?
I'm sorry, it says, is that bounded along?
It is bounded above.
Bounded above, so.
So a sub n is less than or equal to L for some L, for some constant L. And I chose it to be the least number. You guys check this sequence out. How about a sub 1, a sub 2, a sub 3, a sub 4? That is a sequence. I'm not being very careful which one it is. If I wrote the same darn sequence without writing the commas in between, but put plus signs in between, it's no longer sequence. I will use a whole new word for that. I'll call it a series. Because my dot 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 garbage is going to be an infinite series, corresponding to the above infinite sequence. So think of the word series as just representing a sum. David?
Like a sequence was, for the most part, like an arithmetic sequence or an arithmetic series was an algebra, and the geometric series that we go in depth here in 31. What is the product series in comparison? Is that beyond the scope of this course as well?
I don't know what you mean by the product series.
Well, the ones that we were talking about, the capital Pi.
Well, that's just a way of representing a product. I wouldn't
Yeah.
call it a series though, because it's not a sum.
Is it a product rule?
I don't use a product in exactly the same way I use a series. Matter of fact, the reason why the series is so important for you and I is I'll be able to just represent transcendental functions, maybe even transcendental numbers, in such a way that it's going to be represented as a sum.
What is the significance of the product one?
Well, even looking at the factorial, I mean, it can be described in terms of a big product.
Okay.
A lot of counting processes, particularly combinatorics, are really nice looking at that way. That's why factorial is so important.
Gotcha.
Well, that's why factorial is so important at this level of mathematics. So you guys, let me come in. Let me talk about a whole new, be careful by words, a whole new sequence. How about S1, S2, S3, S4, on down. Maybe down to S of n. Now, I'm going to build for you from the previous series a whole new sequence of items, and here's how I'm going to do it. S sub 1 is merely going to be the sum of the first item. In other words, I'm being silly. It is the first item. S sub 2 is going to be the sum of the first two entries of that infinite sum over there. S sub 3 is going to be the sum of the first three entries. I can count. And I think all the way down to the nth term of this whole new sequence is just A1 plus A2 all the way down to a sub n. If you insist, you can think of that this way. I just maintain that this is an infinite sequence that I'm building. So I got a whole new name for it. Given an original series over there that's infinite, I'll refer to this whole new sequence, the S of n's, as a sequence of partial sums. So, definition, man-made definition, nothing to prove here. Given an infinite series. This series converges. And converges to some number called S. If the sequence of partial sums converges to S as well. S is just a finite fixed real number. So for you and I to determine whether or not an infinite series converges, we're going to take a peek at the limit of the sequence of partial sums. That is a sequence, even though I started off with a series. And now you know what the SMIs really represent.
Is that a special way of spelling converges, or is that just
My abbreviation,
Abbreviation.
CBGES. Just be my usual lazy fashion. Now, I think there are some special types of series you and I can determine whether or not they converge. Here's a couple of, well, actually, let's just start with one of them. It's a very special series. Something of the form, shoot, you guys, I gotta slow down. I really have to slow down because your author's notation is a little bit different. I think he refers to the series of my A times S sub K as K ranges from 1 to, sorry, he doesn't. He thinks it's A times R to the K as K ranges from 0 to N minus 1. You guys, I'm so sorry for being so slow and clunky. It's just that I don't think of it this way. But I just want to try to maintain his kind of notation. He likes to start K equals 0. I like to start at a positive 1. In the end, it means the same thing. You check out what this looks like. I think this looks like, I don't know, you tell me, what's the very first term? What's the second term?
AR?
What's the third term?
AF squared.
What's the very last term? Now, the reason why I like to stop at n minus 1 is because the number of terms I have sitting in front of me is nothing more than n terms. Because the very first term does not involve a factor of r. But I do have n terms in front of me. Sometimes I might think of this S of n. Sometimes I might say in English, this S of n is an nth term in the sequence of partial sums for this infinite series. One that kind of looks like an A times R to the K, as K ranges from 0 all the way up. Matter of fact, if you look at this finite series, this term is just its predecessor times 1. Well, this term is its predecessor times r. This term is its predecessor times r. Therefore, I'll subclassify this as a finite geometric series that corresponds to this infinite geometric series. So what I would like to do,
Say that again.
yes, this is important. I maintain that this right here, this expansion, or this, they're all equal to each other, is merely the nth term in the sequence of partial sums generated from this infinite geometric series. I'll refer to this sometimes as a finite geometric series, and this is an infinite geometric series. But this certainly is the nth term of the sequence of partial sums. And therefore, for me to determine whether or not this infinite series converges, back to my definition, I'm going to give up. I'm going to go back to the sequence of partial sums and see if it converges as a sequence, not a series. Let's give it a shot. Given this infinite series, this geometric one, let's talk about S of n. I maintain my S of n looks like this. A plus AR plus AR squared plus all the way down to the last term, which is AR to the n minus 1. Here's its predecessor. Here's its predecessor. There's the nth term, my sequence of partial sums. Well, you guys, that was so much fun. Can I do that again? S of n equals A plus AR plus AR squared plus all the way down to this. You guys, that looks a little boring. Can I change it a little bit? Let's take